For our project, we work on fair race detection, where we explore mitigating visual bias in CNN models. There are well documented differences in the breast scans of Caucasian and African American women, as well as the onset of breast cancer in these races. Our work tries to understand these differences in breast anatomy and how they relate to breast cancer development. For our dataset, we had mammograms from around 5,000 patients, with each patient having 4 mammograms for each of the 2 views and 2 sides. For our initial modeling, we experimented with various architectures before settling on a ResNet 50 body and a custom head. On our validation data of around 1,000 patients, we were able to achieve a classification accuracy of 82%. However, an important observation was the existence of bias in the modeling results. We could observe that the model performs better for African Americans in the higher BMI regions and better for Caucasian in the lower BMI region. Given that the focus of our project is on identifying the differences in parenchymal patterns, it's important that the model does not focus on BMI for discriminating the races. Therefore, for our project, we focus on 2 parts: mitigating visual bias and improving CNN explainability. Fairness is an important problem to tackle in machine learning right now. However, most methods focus on removing bias, dwell with tabular or text data, and not so much on images. We explore a new method for masking sensitive information from image data to mitigate bias in these models. We achieve this by doing adversarial training with the following architecture. We extract features from a backbone network and combine it with a custom head to perform race classification. However, as we don't want the features to contain information on BMI, we also pass these same features to an adversarial network, where the adversary tries to predict for the BMI. The adversarial loss is then used as a negative component of the race classification loss to remove BMI features. The training process for this network consisted of 2 steps. In the first step, we train the adversary by freezing the backbone network. Then, we train the backbone and the race classification head by backpropagating the race classification loss as well as the adversarial loss. Over epochs, we can observe the adversary losing its ability to predict BMI from the backbone feature, and hence we see the adversarial loss increasing. Eventually, we see the bias metric falling from 0.6 to 0.38. Yay! For the explainability of our model, we explored 3 different paths. We used GradCam, a common visualization toolbox, to plot regions of interest as identified by the model. One of our hypotheses was that different elements in the final feature vector of the ResNet model were responsible for capturing key visual patterns. We tested this by identifying feature elements that were strong predictors of either races, and then identifying images that strongly activated these features. For 2 such features with strong predictive powers, we could observe that both features identify visibly different tissue patterns. In the next method, we use soft attention over ResNet blocks to visualize the regions of interest. By adding attention modules to the ResNet architecture, we could observe an increase in accuracy of about 1.5%. One of the key observations was the variation in attention maps over increasing layer depth. While layer 1 attention maps focused more on the overall boundary of the breast, layer 3 attention maps focused on the intrinsic details within the breast tissue itself. One of the difficulties in training ResNet with medical images was the differences in the domains of ImageNet data and mammogram images. To tackle this, we employed different techniques during the fine-tuning process. We added additional dropout layers within the ResNet architecture to prevent overfitting. We also added an additional max pooling along with the existing average pooling layer. Finally, we used differential learning rate, where we had a high learning rate for the head and a lower learning rate for the body. Finally, to conclude, our model's ability to differentiate between races based on mammograms alone help us demonstrate that there do exist differences in the parenchymal features of breast tissue of Caucasian and African American women. We have demonstrated that adversarial training can be effectively used to remove visual patterns that directly contribute to the bias in deep learned systems. We believe that this system can be effectively used to mask sensitive visual information like skin color, gender, etc. from machine learning models. Using feature interpretation, we can identify vector features that correspond to clear, distinct visual patterns, which in turn can act as strong discriminators of race. Finally, we observe that adding attention modules to existing architectures is an effective way to gain insights into the decision making process of CNN models.